So in the last video, we introduced this sort of idea of trying to think more generally about what the sort of governing equation might be for some physical quantity in multiple dimensions. And we sort of introduced the idea that one way to think about that is to ask the question for some sort of arbitrary surface. If I ask the question how much stuff is inside of that surface, I can integrate through that, across that volume, the density of the stuff to figure out how much stuff there is. And if I think about how fast the amount of stuff inside the surface is changing, it's going to change according to how much stuff it's leaving. In other words, according to how much flux there is. And the amount of flux coming out of that surface, I can determine by basically integrating across the surface whatever the flux density is. Okay. So what I want to do in this video is now connect that to a sort of differential framing. So I'm first going to write that integral framing out much more just carefully as a sort of single line. So again, we're integrating over this volume V, and we're basically asking the question, how much stuff is there inside that volume? What's the density of stuff integrated over that volume? And we're saying that the rate of change of that amount of stuff inside should be the negative of the integral over the enclosing surface. So this volume is enclosed by some surface S of the flux density that's coming out of that surface. So we've got this surface integral, and we are taking the dot product and calculating that flux. Okay, so that's our starting point. Now what we're going to do is exploit the divergence theorem. And when we exploit the divergence theorem, what we're going to take advantage of is the fact that when you do a surface integral, you calculate the flux, that could also be written as calculating an integral over the entire volume of the divergence, because you remember that the divergence is simply flux per unit volume. So if we actually integrate the divergence of this flux density over the entire volume, what we should get is the same thing as the actual flux. So this thing, by the divergence theorem, is the same thing as the integral over the volume of the divergence of that flux density dV. All right, so I can rewrite, having exploited the divergence theorem, I can rewrite my right-hand side as an integral over the volume. Okay. And now at this point, my life becomes a lot easier because I can see that I've got a volume integral on the left-hand side, a volume integral on the right-hand side. The time derivative I can simply bring inside. I can do that integral, that derivative either before or after I do the integral. And so it must be the case that the partial of the local density with respect to time is equal to minus the divergence of the flux density. So we now have a very general sort of statement about what is locally true as opposed to what is sort of true for some sort of large volume. But this is saying locally the same thing. It's basically saying if I think about a small chunk, right, the time rate of change of stuff inside this chunk depends on what the divergence of the vector field is in this region. So if they've got a vector field that looks like this, where it's sort of pointing outwards, that's a positive divergence. That corresponds to df by dt being negative, right? If I have a vector field that has no divergence, so say I have a vector field that looks like this, right? This vector field has zero divergence, so df by dt would be 0, right? I've got just as much stuff coming into the little box as going out of the box. And if I think, on the other hand, about, say, a case where I've got a negative divergence, so here's a case of a vector field that has a negative divergence, right? You can see that I've got more stuff coming in than going out. So the time rate of change of the stuff inside the box should be increasing, right? So in this case, the partial of f with respect to time is less than 0, partial of f with respect to time is equal to 0, and partial of f with respect to time is greater than 0 in this last case. Okay? So conceptually speaking, at this point, you can see the sort of connection between this kind of integral formulation, where we're talking about a volume and a surface, and thinking about the amount of stuff going out of that volume relating to how fast the amount of stuff inside the volume is changing. And we've changed that into a sort of differential statement, but it's a statement that's basically saying the same thing, that the time rate of change of the density of stuff has to do with the flux density in that with the divergence of the flux density in that region. So it's really the same idea, but just expressed in a differential form. In the next video, what we'll do is finally try to connect this to a kind of stock and flow picture of these kinds of systems, so that you can make that connection between both the sort of ModSim version of this and the Linearity 2 version of this, and hopefully get a little bit more insight into how we think about sources and sinks as well.